Well, thank you, Brice, and thank you all for showing up and for having me here for this 2 days. I'm going to talk today about a project I did with, I'm still working on with Scott Tremaine at the IIS about the possible dynamical origin of orbital properties of exosolar planets. So to give you kind of an overview of how this talk is going to look and where this is going, the context of what I'm going to be talking about is understanding planet formation and evolution. So the big picture, the big goal is to understand how planets form, what kind of planets form, how do they evolve after formation, and the things that we observe now, basically what's out there, how the solar system formed, and how the other planetary systems are formed. Now, to understand this, we need to understand the properties of planetary systems as we observe them today. And because of the ways that planetary systems are discovered, most of the parameters we know for most of the planets that we know of outside of our own solar system are just dynamical parameters. So orbital parameters like sine major axis and their mass, their eccentricity, and the topic of today's talk that I'm going to be discussing is I'll pose a simple question: to what degree are these observed properties of exoplanets a product of long-term dynamical evolution? The tools how we study this are simulations. So we simulate large ensembles of planetary systems. We simulate dynamical evolution in these ensembles, and then we compare this to observations and compare their initial conditions to what we expect from planetary formation, and try to infer some conclusions from there. And the observables that we have are eccentricities, inclinations, and number of planets in the discovered planetary systems. I'm going to mostly be concentrating on eccentricities initially and then say something about the rest. The whole point of this is to come up with some implications for planet formation, which is a notoriously difficult and still unsolved problem, and to produce testable predictions of what to expect in the observations if the answer to this question turns out to be that dynamical evolution really is relevant in studying the observed properties of exoplanets. For those of you who are not in this field, let me just give you the quick explanation of what the problem is. So this here is the solar system, again with 8 planets as it was up until 1930. The typical layout of the solar system is what we used to think this is what we used to think that exosolar planets would look like, the exosolar planetary systems would look like as well. So mostly circular orbits, small eccentricities, so less than 0.05, small inclinations, just a couple of degrees, giants on the outside, terrestrial planets on the inside. And another thing, it's dynamically stable over long time scales, at least over a couple of gigayears. This picture of our universe, based on the solar system, has started changing with the discovery of planets around main sequence stars. So in 1995, starting with these two guys here, they found the first exosolar planet orbiting a solar-type star, and in the years since, there have been 250 exosolar planets discovered. Most of them are still discovered with the same technique as the first exosolar planet, so with radial velocities by observing reflex motion of the host star. But recently, some planets have actually started, some groups have actually managed to do direct imaging of planets that are further out from the star. This is the problem. So if you remember what I've shown you for the solar system, this is the distribution of eccentricity, sine major axes, and masses for the planets outside of the solar system. They're very different from what we see in the solar system. So for one, I've circled a couple of regions of interest in these diagrams. First planets that were discovered were hot Jupiters. That is this little group here. They're planets of Jupiter mass and of a couple of Jupiter masses very close to the star, small eccentricities because of tidal circularization. That's why you don't see any of these planets in this region of the diagram. And they're in orbits that with periods on order of a couple of days, so 3 days, less than 10 days. These we don't see in the solar system. Second, and the thing that I will be concentrating on in this talk, are planets with high eccentricities. So we have planets of Jupiter mass. So these are all in Jupiter masses, and planets going up to tens of Jupiter masses with eccentricities that in the solar system we'd usually ascribe to comets or strange asteroids. So eccentricities of 0.4, 0.6, and I think the current record holder is 0.91 or so. Solar system is not like this, which is fortunate for us because it would probably be very difficult for it to support life if it had massive planets on eccentric orbits like we see in the exosolar systems. To complete this little tour through the properties of exosolar planets, their mass distribution goes something like 1 over m. So lots of low mass planets. Observations become incomplete at this end. Their same major axis distribution is shown in this diagram. It's approximately consistent with being flat in log A. Now, the question that's been on everyone's mind for more than a decade now is why? So why are the observed properties in these two diagrams the way they are? And it still is not quite clear. There still is no universally accepted explanation, but this is not for a lack of trying. So what I'm showing here is just a small subset of various papers and various authors who have touched upon this topic. When we talk about the origin of these properties, it's useful to separate. It's useful to think about so where these properties came from. It's useful to separate the evolution of planetary systems into two more or less distinct phases. One, we know that planets have to form, that these types of planets, Jupiter masses and a few Jupiter masses, have to form on relatively short timescales. So the actual planet formation lasts only a couple of million years. This process is very poorly constrained, and people like Andrew and Yoram can tell you all about this, but the physics here is very hard and difficult. But the only thing we know is that the process is relatively fast, so it lasts for a couple of million years, and it may possibly lead to systems that are unstable on longer timescales. But this is ultimately what we would like to understand, this stage 1 planet formation. After this happens, there is a few orders of magnitude more of dynamical evolution that these planets go through. So the end of this process is what signifies the end of this part of planetary systems' lifetime is essentially dissipation of protoplanetary disk. So when the disk becomes unimportant, we say that they pass from stage 1 formation to stage 2 evolution. The evolution lasts for a couple of billions of years. So the evolution is defined as the time as the time from when the planet formation ended up until where we observe the planets. And we observe these planets around solar-type stars that are typically a few billion years old. The physics in this phase is easy. The disk has cleared. The only thing that essentially affects the planets is just good old Newtonian gravity. And it's the system, if it's initially unstable, because remember, it forms on relatively short timescales, and a priori, there is no reason for it to be stable on gigayear timescales. If it's unstable, it's going to relax in the stable state in this part of its lifetime. And again, these are the systems we actually observe. However, despite the relative simplicity of this part of their lifetimes, and despite the fact that it lasts much longer, thorough investigations of this stage 2 have been surprisingly rare, or usually they have been oversimplified with just taking a few planets or adding in additional conditions to make the computations simpler. So what we do, and what is typically the way to investigate this stage, is you generate an ensemble of mock planetary systems that then you put into an integrator and integrate over long time scales and compare the results to observations. There we have a problem that if you want to generate an ensemble of planetary systems, you need to come up with some initial conditions, with some reasonable initial conditions. Optimally, you would want to take those initial conditions from some theory of planet formation. The problem is we still don't have a theory of planet formation that's predictive enough to tell us, for example, what kind of planetary system do I expect to come out of this protoplanetary disk once it disappears. The other way you can do this is you just take the observed planets and take those as initial conditions. And the third way is just to start with random initial conditions and see what happens. Now, the last way may seem a bit hopeless because this is a problem with lots of free parameters. So to start with random conditions and hope that you wind up with something that resembles the observations may seem hopeless. But under some assumptions, which I'm going to touch on later on, starting with random conditions may not be such a bad idea after all. So when you choose your initial conditions, numerically evolve these systems over long time spans. So typically what we do is we evolve them over 100 million years. We did some over a giga-year, but it seems that for initial conditions we started with, everything that's interesting happens on order of 100 million years. And then identify and study common properties, the processes that cause them, and compare this to observations. So I'm going to jump straight to numerical experiments. What we did so far was to create eight ensembles of 200 to 500 systems each, typically. So typically what we do is we define an ensemble as with some distribution of orbital elements of planets in the planetary systems that constitute that ensemble. So let me, for example, take this one here, C10S10. So in this ensemble, we generated planetary systems where each planetary system initially had 10 planets. We drew the initial eccentricities of these planets from a Schwarzschild distribution, which is basically 2D Maxwellian distribution with sigma of 0.1. So approximately the peak is at about 0.1 eccentricity. We drew the distribution of inclinations from the same distribution of same shape with the peak at about 6 degrees, and we initially spaced the planets uniformly in log A between 0.1 AU and 100 AU, and we did the same thing for their masses. So we picked the masses between 0.1 and 10 Jupiter masses. In this way, we construct, in this case, 200 planetary systems, and then we integrate each of these planetary systems for 100 million years. The distributions of mass and 7 major axes were motivated by observations and in part by theory. Specifically, Ford et al. Showed that who played with similar games but just using 2 or 3 planets in a system, they showed that one of the key things if you want to get results that are similar to the observations is that you cannot start with planets of equal masses. So guided by that, we chose to use the distribution that is flat in log m, which is also comparable to observations. Most of these systems are crowded and initially unstable. And this is intentional because what we want to do is examine what dynamical instability and what dynamical relaxation does to these planets. If we start does to these systems. If we start with a stable system, we will end up with a system that will not change appreciably at the end of the integration. So to give you a feeling of what typical evolution looks like, This is a plot actually, not from these simulations, but from Chatterjee et al., who looked at 3-planet systems. Our plots look virtually exactly the same like these, but are not as nicely colored as this one. But this is the typical behavior of eccentricity and semi-major axes in these simulations. So what you have is a planetary system that starts off in an unstable configuration. Its orbital elements start varying randomly, chaotically evolving. So what you see here is the semi-major axes. And then at this point, the red planet ejects. So the black planet has a close encounter with the red planet, and the black planet is ejected. And then the system is left with only 2 planets that are far apart and that are stable, and the only thing you have is this evolution of eccentricity down here. Another more complicated example is where you have, again, starting with a 3-planet system. You start with 3 planets, then the inner 2 actually change places. Then the outer 2 change places as well. What are now the inner 2 interact and collide and merge, continue with little change in their orbital parameters except for eccentricity. However, they pump the eccentricity of the outer planet, and in the end, the outer planet gets ejected, and you're left with a single eccentric planet. So typically, you see that even when you start with just small eccentricities. You go through a lot of changes in eccentricity, a lot of evolution, and you wind up with eccentricities that, in this case, for example, it's closer to 0.28 or so relatively high. Sorry? These are orbital timescales, so this is 10 to the 3. So in this case, this is a system that is extremely unstable, so the evolution happens rapidly. We see the same thing if you start them farther apart. We see the same thing happening, so same qualitative behavior, just on longer time scale. This typical behavior is summarized for entire ensembles in this plot. So what I'm showing here is the average number of planets per system versus simulation time. So you see most of the ensembles with simulators started with 10 planets. There was one with 50 planets and one with 3 planets. And all of them show rapid drop-off, rapid loss of planets on secular time scales, and then leveling off after about 10 to the 60, 10 to the 7 years, leveling off of this drop-off of planets at a value of between 2 and 3 planets. So on average, no matter with how many planets we started in these systems, they ended with about 2 to 3 planets, which means that a substantial fraction of them was removed mostly through ejections and some through collisions with the star, very few through mergers.
The time scale here somewhat inconsistent. There's formation happening on 10 to the 6 years. You can't sort of remove something and then suddenly in 10,000 years something drastic happens.
Oh, this is an artifact of a simulation in a way, because they were set up in initial state which is too unstable. As I say, if I relax this condition, and that's what those are simulations that we're doing now, it just prolongs the time until the first instability starts happening. So what we imagine may be happening is you have planet formation, you have the disk that kind of stabilizes the system. If the disk disappears on relatively short time scale, you may leave the system unstable on, let's say, a factor of 10 longer time scale, and that's when this might start happening.
Yeah, it is safe to say that if your initial conditions were less violent, then you might wind up with systems that could hold on to larger numbers of planets.
That depends on it isn't actually the case. It is true that this average number rises a little, but not as much as you would expect. So it's hard. It depends on how violent the instability is, I guess.
What's again the range? You showed this in your plot. What's again the range of masses?
Is from 0.1 to 10 Jupiter masses. So it's basically, there's a giant of the likes that we observe today.
Did you do simulations with smaller mass
We're doing those now. But for smaller mass planets, they will not have, I doubt they will have much effect on the higher mass planets. However, it will be interesting to see what the higher mass planets do to the lower mass planets and whether we can reproduce the observed mass distribution as well. So let me talk about the eccentricities. The eccentricities in observations are supposedly the least biased measured parameters. So this is the spectrum of outcomes that came out of the simulations, out of these 8 ensembles that were simulated. And apparently this seems like more or less a mess. So what I'm showing here is the distribution of eccentricities in each ensemble, and the width of this band is plus or minus 1 sigma, where sigma is just the Poisson noise due to a finite number of systems in each eccentricity band. However, if you kind of take a look at the various distributions, you can come up with a rough classification based on the degree of mutual similarity. So, for example, look at these 4 down here, which are very similar, and based on the degree of evolution from initial conditions. So, this distribution of this ensemble here, basically, it started with 0 eccentricities, and it didn't move much from its starting point. So we label these 3 classes as inactive, active, and partially active systems. Or inactive, partially active, and active systems. The class of active ensembles is what I'm going to be concerned with for most of the talk. So the interesting thing about these is they show a very good degree of agreement for planets at high eccentricity, so above eccentricities above 0.2, both mutually, so they're all the same in this range, and with the observational data. So the histogram here is the distribution of eccentricities observed in exosolar planets. And this is despite the substantially different initial conditions that these ensembles started with. So if you take a look at this plot, it's a bit busy, but just pay attention to solid lines. Solid lines are the initial conditions, the initial eccentricities of these 4 ensembles. So see there's one that starts with initial eccentricities of about, I believe this is 0.05, Schwarzschild distribution. There's one that we started with a flat distribution of eccentricities all the way from 0 to 0.8, and there are some in between. So all of these converge to the same final eccentricity distribution down here. And that distribution is similar to the observations. Now we can check this quantitatively. These are the p-values for the KS test, for 2 sample KS tests between all of these between the distribution of these ensembles. So these are the mutual. This is the test of mutual similarity. So you see when we compare the entire distributions, the 3 out of 4 of these ensembles are given according to this KS statistics are similar to basically any significance, any reasonable significance level you take. The ensemble that started with 50 planets is a bit worse because it actually has a more high eccentricity planet than the others. If you limit yourself only to high eccentricity planets, then you get a much better agreement. This is the bottom plot. So planets going from 0.2 eccentricity 0.2 above, and especially interesting is that this is also the distribution that we see in the observations. So they're a good match to the observed distribution of high eccentricity planets. Now, there still is this problem with the excess of observed low eccentricity planets. So this is how the observed distribution looks like. And this is the best fit distribution. This is the best fit active ensemble distribution compared to it. So we have an excess here of about 25% of planets that above what we would predict if if all exosolar planets are formed in the same dynamical process as the four ensembles, over here. Oops. Now, this access here must, if this agreement means that this is the process that's producing the high eccentricity planet, the access here has to be produced by a different mechanism, because it cannot be produced by relaxation, which is responsible for the shape of this curve, as I will argue soon. A few other things. We can look at correlation of eccentricities in simulations and in observations with other observables. So two things we did was look at correlation of eccentricity and semi-major axes. There is no correlation in the observations, and there is no correlation in the data as well, except for the planets that are at the very edge of our range of semi-major axes, and these are planets in highly eccentric orbits, which you may think of this as just an artifact of initial conditions, because there are no other planets over here in the initial conditions. As far as the correlation with the mass of the planet, in the simulations we see a little or no correlation. So the most we see is in this ensemble, where there's a slight positive correlation, especially in the high mass planets. In the observation, the current observational picture is that there seems to be small positive correlation. So the high mass planets seem to be, on average, seem to have slightly higher eccentricities than low mass planets. But this picture has actually been changing a lot as new planets have been discovered. So it's not quite clear what part of this is real and what part of this are the biases. So what are the active ensembles? For now, I just presented them as this class that we picked out because they looked similar. And I will argue now that these are the ensembles whose system orbital properties were entirely set by dynamical relaxation and who have zero memory of their initial conditions. We looked at distribution of number of planets versus eccentricity. We didn't look at that because, well, the distributions with same major axis are observation. You can't really compare them to observations. That's the main problem, because observationally, distribution of same major axis is extremely biased. So we can do that in simulations, but even if we did that, we couldn't really compare it to observations because the observations are biased. Sorry?
Do you know roughly how many you are in the same axis?
Well, we do, but I mean, it's then better to compare that to compare it versus, for example, the radial velocity amplitude, and look at distribution in that space, because that is what's actually measured. So that's a less biased quantity. I'm not sure if that answered your question, or yeah.
You could check that also.
Yeah, I mean, at some point I did like all of these plots of one versus another, but so the ones that I'm presenting here are kind of the ones that had most information as far as comparison to observations are concerned, or are interested in some way. But I can show you those after the talk. There is a deficit of planets at small semi-major axis in these simulations, for example, compared to the initial conditions. But that distribution is going to depend on the initial conditions a lot. So that's another reason why I'm not sure how meaningful that number would be, because if I start with a lot more planets, with little planets in the inner part of the planetary system, I'm not going to get more of them there, usually. Yeah. I have plots like the one you're interested in, but I can show that to you after the talk. So going back to this question. to explain what I mean by this is note that not all systems are created equal. You can have a planetary system that is stable, which is you lay out its planets and it doesn't change ever. You can have a planetary system that is unstable, but then it can be unstable with short time scales, which in my case means a few million to tens of millions of years, or it can be unstable on long time scales, like the inner solar system is potentially unstable on time scales of hundreds of millions of years. Then this here is a general property of any system going from 2 planets out to how many planets you want. And your system can also be crowded, meaning have lots of planetary systems that are close by. And you can also have systems that are not crowded. So, for example, systems with 2 planets, 3 planets would not be crowded in the way they're defined here. What I'm going to argue is that our active ensembles are systems that are crowded, have lots of planets, and are short-term unstable. And that leads them to dynamical activity. Now, to quantify this, we have to introduce some measure of dynamical activity, and that basically comes down to the question of how close is your planet to another planet in some reasonable units that tell you how much the other planet perturbs the orbit of whatever planet you're observing. So we introduced this measure called the Hill separation, which is defined as the distance from a planet to a planet that is more massive than the planet you're observing, and that is closest to it in terms of its Hill radii. So Hill radius quantifies the sphere of influence of any given massive body orbiting the star. And in this case, for example, in this example, I'm showing a planet outside on the orbit outside here. There's this, and there are 2 smaller planets on the inner orbits. And the point of this is to show that the outer planet, in terms of this definition, is the Hill neighbor of both the inner planet and the middle planet because of its higher mass. So all of these 2 planets are geometrically closer. It's actually the outer planet that exerts bigger influence on both of them than they mutually do. So this is assuming that there are, I'm looking at short-term stability here. This is assuming that there are no resonances between these 2 planets which would change the situation dramatically. To give you an example for the solar system, these are the planets in the solar system. This is their distance in these mutual Hill radii to their Hill neighbor, and this is their Hill pair. So for most of the planets in the solar system, in terms of this definition, the planet that perturbs the most is Jupiter. And the median Hill separation in the solar system is 21, and if you observe giants only, it's about 15. Now, if we apply the same thing to the simulated planetary systems, this is what we get. So what I'm showing here are medians of Hill separations for the 8 ensembles we integrated and how they change through time. So you can see that there are some which start essentially with 1 planet on top of each other. So this very small hill separations down here. There is a group that starts with Hill separations at about 5 Hill radii, and there's only one that starts with separation of 14, so with relatively high compared to others. All of these evolve, so these 2 groups, both of them evolve to separations between 12 and 15 Hill radii. And remember, this is a point where most of the dynamical activity stops in this system, and for practical purposes, they may be considered stable once they get here.
Is this measured at closest approach?
This is actually the distance between their orbits. So this is, you take when they're closest together. Yeah, so we take 2 orbits and then find the distance, the closest distance at the orbit. So we approximate the planet as being smeared out over orbit. And this is, again, in 3D, because inclinations of these planets can be non-negligible. So it's a relatively complicated definition, but it works. So take a look at this plot, and this is what it corresponds to. So these four ensembles that are grouped down here are the four ensembles that we classified as active. The three ensembles that are grouped over here are the three that we classified as partially active, and the one that was up here that didn't change its hill separation much was the one that was inactive. So I argue that this is a sign that these guys here are a product of dynamical activity, and that this is why these eccentricity distribution look so similar, despite them starting from different initial conditions. Now, you may wonder, okay, but they all, both the active and partially active systems end up with approximately same median hill separation. So why aren't these guys here? Why don't they have the same distribution as these ones down here? To understand what's going on there, we really have to look at the entire distribution of hill separations and how it evolves through time. So what I'm showing here is the whole distribution, so not the median. Now this is the entire distribution. This is for one active ensemble. So the distribution at t equals 0 is strongly peaked at hill separations less than 1. As it evolves, what you see is relaxation through removal of planets at small hill separations. So notice how this peak becomes lower and lower, and how basically this region here gets cleared out. So a region between 0 and about 5 hill radii gets cleared out of almost all planets. So nearly all planets at small separations get removed by 10 to the 7 years. And the second thing is nearly all planets have started from this peak. So most of the planets that form this peak in the end have started from this large peak in the beginning. The final settling is at a peak of about 12 with full width of half max of 8. So the planetary systems reorganize from this initial configuration to a configuration like this to maintain this type of separations between the planets in the stable configuration. Now, if I take a look at snapshots of just initial versus final hill separations for all ensembles, this is what I see. I see a similar story for the other active ensembles. So they started with a strong peak at 0, and then wound up with this peak at, what is that, 14 or so. Virtually all of the planets that were here were cleared out. But take a look at the partially active systems. So partially active systems have already started with a peak that is approximately at the same place where this final peak is. So in their initial conditions, they already had planets that were here, and they had a fraction of planets that were on lower separations. These planets, these systems that were on lower hill separations, got cleared out, got reorganized, and moved to this peak, just as it happens with the active ensembles. But in this peak, there was already a piece left over from the initial conditions. And that piece that was left over from the initial conditions carried memory of initial conditions with it. So that is the reason why in this plot, this final distribution here has a tail that looks remarkably like the tail of the active ensembles, and that tail was produced by the same process as the tail in the active ensembles. But it also has this piece here, which is the remnant of initial conditions of basically those systems that were already stable when we started the simulation. So the summary of main points so far is that the active systems are those whose eccentricities were entirely set by dynamical relaxation. As you've seen, they all of those systems got reorganized. There's not a single one that remained similar to its initial conditions. They retain no memory of their initial conditions, and that's why their inclinations are their eccentricity is virtually the same. They finish with the same equilibrium eccentricity distribution, and they correctly describe the distribution of high eccentricity planets, so planets that eccentricities of more than 0.2. So you can that cut is flexible. So if you take 0.3, it's going to work equally as well, 0.4. But basically, less than 0.2 is where there's an excess, and due to that excess, we don't claim that it's 100% of observed planet can be explained with this, but it's 75% of observed planet are in this category once you exclude hot Jupiters. And hot Jupiters are, the reason why I exclude hot Jupiters is they're basically dynamically irrelevant for this type of study because they're in 3-day orbits. They're virtually entirely detached from the rest of the system. So if you assume that they got there through migration while they were still disk, then the rest of the planetary system is not even going to know that they're there. Although I'm going to come back to that a bit later. Let me talk in these last few minutes about some consequences of this. One thing is inclinations. So you want to find something else that you can measure that is a consequence of this model. And one thing is the distribution of inclinations that you expect in the observations. Now, the way inclinations are usually defined, for example, in the solar system is you define them with respect to the invariable plane, or you measure mutual inclinations between the planets. Now, this is something you still cannot do with exosolar planets because we don't know what the angle of their orbits is on the sky, nor we can't even define the invariable plane because we don't know what all planets are there in a given exosolar planetary system. What's better to do for the purposes of comparison with observations is look at the inclinations with respect to the plane of initial conditions, because you can. This is observationally accessible if you identify the plane of initial condition with the plane of in which the star rotates. So the normal to the plane of initial conditions, which you assume is the plane of the protoplanetary disk, is the same as the spin axis of the star. If you make that assumption, then the measurements of misalignment of disk of planetary orbits and the stellar spin is exactly this inclination I sub r, that is the inclination with respect to the initial plane of initial conditions from which the system started. So if I do that, what I'm showing here are cumulative and differential distributions for inclination as defined with respect to the variable plane and inclination defined with respect to the initial conditions. And what you're seeing is that there is this dynamical relaxation causes a substantial fraction of planets to attain relatively high inclinations. Now remember, in the solar system, all giants have inclinations on order of 2 degrees or so. What we're seeing here are the medians, which are dependent on the initial conditions because the distribution of inclinations is not relaxed. But the medians are on average between 7 and 10 degrees. And specifically 10% of planets, so 1 in 10, should have this misalignment more than 25 degrees. You can do all sorts of, you can also observe, look for correlations between inclination and mass at the same major axis. There are some weak correlations, but nothing important for now. But the point is that this is observable, and that recently there's been one measurement. So most of the measurements of this parameter have been done on hot Jupiters, and I think there are in total 5 measurements for hot Jupiters now, and all 5 are consistent with there being no misalignment between the stellar spin and the normal to the orbit of the planet. There have been 2 planets which are not hot Jupiters, which have eccentricities. One has eccentricity of 0.5. The other has eccentricity of 0.67, I think. The one with 0.5 is also consistent with there being no misalignment. The one the other one has a tentative measurement of misalignment of 62 degrees plus or minus 25. So now note that these are huge error bars, and these authors actually in their paper have, I mean, even in their title, there's a huge disclaimer. I think the title is something like candidate misalignment or so. But if this measurement holds, then this will be the first planet where we know that it's significantly misaligned compared to the stellar spin, and this will imply that there really are some kind of strong planet-planet or planet-star interactions. And incidentally, this star is not a binary going on that are pumping up this inclination. So getting a sample of inclinations of few tens or few hundred planets is going to be extremely informative in any case, irrespective of whether this entire theory works or not, because even if it does work, what we see here is that inclinations are dependent on the initial conditions as opposed to eccentricities. They still depend on how you started the system. Another consequence is the expectations for multi-planet systems. So this is the number. What I'm showing here in the top plot is the number of systems with a given number of planets. So and this is a typical for all active ensembles. So what you see here is that that most of the systems have 2 planets and 3 planets. There are very few systems that have 4 planets or 5 planets, and virtually no systems that have more than that. So the generic prediction is kind of if there really was this violent stage of relaxation early on after planet formation, there will be few systems with many giants. And secondly, the average eccentricity of planets in those systems will correlate with the number of planets in the system. So if you see a planetary system with 4 planets, an average is going to have lower eccentricities than a planetary system with 2 planets. Or alternatively, you can invert that and say, if you find a planet with eccentricity of 0.5, then it has a relatively low probability. It has a certain probability of having another planet in that system, but it has a low probability of having an additional second or third or fourth planet, and so on. This is also something that's going to become easily measurable in the next couple of years as larger surveys come online and the baseline extends. Finally, I just want to say one thing about the origin of hot Jupiters. So one of the things we see in the simulations is that about 20% of our objects are lost through collisions with a star. While we don't have, and that means that most of them go through phases where their orbits are highly eccentric and come close to the star, so closer than the tidal radius, and essentially they're subject to tides, and their orbits may be circularized if the timescale to circularization is slower than the timescale to at which their eccentricity is being pumped. This at this point is the interesting number here is that we're seeing that there are about 20% that wind up this way, and this mechanism has been, well, this was the first mechanism that was proposed as an origin of hot Jupiters back in 1996, and it was quickly discarded because the first simulations showed that relatively simple simulations with 2 or 3 planets showed that it cannot produce enough hot Jupiters to explain the number of hot Jupiters that was seen. What we're seeing is when we start with n planets instead of just 2 or 3, and with a more realistic mass distribution, we can have an order of 20 to 30% of planets that actually wind up in the star. So this is an indication that this mechanism may still be viable. Of course, this requires much more careful follow-up simulations that include friction to see whether this is really possible or not. But at least it's not something that can be dismissed out of hand. So, do I have time for like 3 or 4 more minutes? Yeah. Okay. So this is the last. This is kind of my last module of this talk, and it's slightly orthogonal to what I've talked before, but I think it's kind of interesting because, for one, it gave us a few headaches while completing this paper, and that is, you come up with some theory, you want to compare it to the observations. Now, what do you do when the observation change between the time you submitted your paper and the time you want to submit the revised version to the referee? Which is exactly what happened in this case. So, just as we were finishing this, we noticed that there's this paper by Burke et al. Where he remarked that there seemed to be something different between the observed distribution in 2006-2007. Now, this didn't seem very convincing to me, so I took the old data files that I had and made my own plots. And this here is the distribution in April 2006. This is the distribution of eccentricities of observed planets. And this here is the distribution in February 2007. Now, note that over here, there's not much change. So at eccentricities greater than 0.2 or so, it's approximately similar. But at low eccentricities, there's this peak that showed up. And if I just plot the planets that were known before April 13, 2007, and it was actually Friday. That was probably a bad date to take this snapshot. But if I plot this versus planets that were discovered since, you can clearly see, I mean, even by eye, that there's something different between the two. If you do a KS test between the two, so what's the probability of these two distributions being drawn from the same underlying distribution? It's less than 0.2%. So I just wanted to put this up as a note at the end of my talk that there is something funny going on with the planets, with the newly discovered planets, and it's not clear to me what it is. Maybe it's the recently discovered planets are different in some way. Maybe the observational biases are different. Maybe there was something wrong with the data 2 years ago at Exosolar Planet Top Encyclopedia. It would be really interesting to have like an entire snapshot of all possible, to be able to observe how solutions for orbits of all planets change through time to understand what's going on. But it may be as simple as observations going to stars of lower masses and stars with lower masses having planets with different orbital properties than stars of higher masses. So this is more or less the last plot that I wanted to show. And the reason why I included this in the talk was, let me just show you this. If I talked here a year ago, my conclusions would be much more impressive, because this is what the observed distribution looked like compared to our predicted theoretical distribution. And now we have this annoying peak down here. So let me finish with the summary. This is the largest study of stage 2 evolution to date. I'm claiming now that dynamical relaxation to planet-plane scattering is capable of not only qualitatively but quantitatively explaining the observed distribution of high eccentricity planets. And that this model predicts a number of testable and measurable consequences. So non-zero inclinations, small number of average planets per system, correlation between the number of planets and eccentricity, and numerous free-floating planets, which is another thing I didn't talk about, but it's also very interesting. Implications for planet formations are that dynamical state after formation is not necessarily the same as the dynamical state we observe today. That does not have to be the case. And also, if this is really what sets the eccentricities, then planet formation theory should predict that planetary systems form in unstable configurations as they come out of the protoplanetary disk. So I'm going to stop here and take questions, and thank you for your attention.
You might expect that
have not looked at that particular correlation. There is the number of planets versus mass. There is no correlation with the average mass in the system, in the planetary system. So there is a correlation in the sense of what planets are preferentially ejected. So low mass planets are preferentially ejected. But in general, there is very little correlation with virtually any parameter of mass with virtually any parameter, which is kind of surprising.
So I guess your point 6 and 7, I'm wondering if there's a sort of stronger statement you can make. I understand that if the state after formation is the final state doesn't remember the initial configuration, it's hard to say something about what it was. But are there things that you can rule out based on the dynamical evolution that you see? So if I started with a system that looked like this, we would never be able to reproduce an observed system. And can you use that to rule out certain theories of planet formation that people are advocating?
Well, I mean, we can rule out so if you have a theory of planet formation that produces planets exactly with the eccentricity distribution that we observe today, then I cannot rule out, because the corollary of this is that the observed distribution is an equilibrium distribution. If you have if you have a theory of planet formation that produces planets with different eccentricity distributions that do not change, then that is ruled out by this. So I think that is kind of the level at which it works. So I'm not sure if that is a good or bad feature, but the only thing that is required for this kind of to work, I mean, so far as we know from this limited set of simulations, is that the planets are initially unstable. So the planetary system is unstable enough to go through this kind of relaxation. But as I said, there seems to be more information in distributions of eccentricity, maybe in distribution of mass, and that is the direction, the next step that we're taking to research this.
Well, first a comment. If you're right, 75% of the system had gone through such a relaxation, then there wouldn't be any Earth left.
Yeah. I haven't actually put in test particles to see that, but it's hard to expect given the variation of eccentricities. Yeah.
The other thing I'm always wondering is that your as you said, eccentricity, final eccentricity distribution doesn't count than the initial one. But I can always have a sort of reasonably compact system, very, very circular. This is your partially active system, right?
Okay.
So crowded but circular.
Mm-hmm.
So it just satisfies the Q separation to be fall.
Sorry, I didn't understand the question. Or
Oh, so that is putting, like, if you start from initial, if I'm putting a lot of those systems, so you're saying you can smooth the fraction of such a compact circular system to be less than 25%.
So this says that I can. These 25% are systems that have not gone through this type of relaxation process. So they may be either systems that were spread far apart, or that were crowded but are stabilized by resonances, for example.
What about the prevalence, or I don't know how prevalent, of resonances among multi-planet systems?
There are, so that is something that we do not see in the simulations. So we see a few that just by accident get caught up. But in the actual observations, I think 5 multi-planet systems, 5 out of 20, are seen to be in resonances. And this is something like 2-to-1 resonance. And so in actual observations, we do see multi-planet systems in resonances. And so if this is something that we do not see in this type of process, but that is where this 25% becomes helpful. Because we actually, I actually wouldn't expect to see a second planet that close in that system if that system has passed through this dynamical relaxation phase. So the fact that even that it has the second planet that close means that it's not in this 75%. And also their eccentricities are lower on average. So it is consistent with, yeah. So if five of these, if 5 out of 20 multi-planet systems are in resonances, then 15 are not. So.
Well, those 15 may have low mass planets in them, right?
Well, but we don't know that. Yeah. I mean, this is all something that's going to, when we build up the sample, this is all going to be testable, and this is a nice feature that I can actually go and compare this to the data as it becomes available. If it turns out that all multi-planet systems are in resonances, then this doesn't work. So that's easy to falsify that way.
Last question. For your observational biases question at the end, are you including transiting planets bound to your transits in that?
There are, so I did both. So I included and excluded the transiting planets, but the transiting planets are all hot Jupiters. So they're essentially removed by the hot Jupiter cut.
Okay.
There are a few that are not. By a few, I mean 2. So they're the only ones that would be affected.
Okay, so let's thank Mario again.
Thank you.